Alrighty, so yesterday, the last thing that we made it through was this little box. I just wanted to revisit this again, where we're talking about characterizing the nature of a quadratic. And what we want to remember is all of this comes from, we collect a bunch of data, and then we notice, hey, when I look at the scatter plot, this does not look like a line. This looks like a parabola would fit this much better. And so we'd start talking about how we really probably should use a polynomial of degree 2, a quadratic, as we go through that. Algebraically, our calculator is not going to spit out vertex form. Our calculator is going to spit out the standard form of a quadratic, a squared plus bx plus c. We could complete the square, and make it look like our vertex form. But most of the time, if we have nasty decimals and word problems, we'll just use what we know about standard form to find the information we need. Graphically, we'll have a parabola with the vertex at axis of x equals h. Again, that's always for what we're doing right now. Our parabolas open up and down. So it's going to be a vertical line, x equals h, opening upward if a is greater than 0, downward if a is less than 0. The initial value is always going to be that 0c, and then our x-intercepts, we could use the quadratic formula, but for word problems, we're probably going to use the graphic. I'll just let it take care of all the nasty decimals. And that's where we're going today. Day 3 is applications. And applications, of course, mean we're going to do some stuff involving some real-world situations. And like I said, we're going to start all the way from the data and work our way backwards. We actually started this problem earlier on. And this is applications of quadratic functions in economics where demand is linear, revenue is quadratic. With the Twin Pixie model, we talked about how if the price goes up, the number of boxes that they sell definitely goes down. And that was definitely a linear model. But as it says, while that demand was linear, revenue is a quadratic. So revenue becomes a parabola. And that's one of the things that happens with businesses when they try to figure out where should we be producing in order to make the most money. There's our quadratic that has to do with revenue. Now, why is that so significant? Because what a company tends to do is figure out where they can reduce their costs and where they can make the most profit. And what happens is that ends up being a line that's a horizontal line straight across that parabola. And that produces a problem because the company can decide to produce very little of their product and sell it for an increased cost, or sell lots of their product and sell it at a cheaper price. And when we are in a recession or a depression, they always choose higher price, less product. So in good times, we'll see, hey, there's all kinds of these things coming out. Just thinking about, the music, the iTunes and all of that stuff. It's pretty cheap. They decided, hey, we're just going to, anybody that wants it can have it. We'll make this at a reasonable price. But in bad times, you'd probably be looking at, $500 for an iPod. And people would not buy it, at least not normal people. People with a lot of money, yeah, they might be able to pick one up. So what we're looking at is what's going on, where would they want to produce? So here's our model from the Twin Pixie, and they did a little bit of rounding there that we did, but they went to the hundreds position. And it says, develop a model for the weekly revenue generated by those donut-shaped breakfast cereal sales. We should just put Twin Pixie Cheerios. Determine the maximum revenue and how to achieve it. So our little hint here is to find that revenue, which we're going to use a big R for, what we have to do is multiply the price per box times the number of boxes sold. Well, we don't know how many boxes they're going to sell, so that's our unknown. But we did come up with an equation for the price of that box. And I'm going to put the 3 decimal places back up here. It was negative 15,358.929x. And then we had plus 73,622.500, which basically would just be. So if we want the revenue, what we have to do is just distribute gas. The number of boxes sold times the price per box. And that's going to be quadratic. So now, determine the maximum revenue and how to achieve it. Right? So I know it's a quadratic. And they're saying without thinking about minimizing costs or any of that stuff, just use that quadratic to figure out where the maximum revenue is. Well, it has to be at the highest point. I mean, our inputs are our x's and our output is the revenue, so it has to be at the vertex. Now, we could sure put that into the calculator if we wanted to, but we know how to find the vertex when we have a quadratic. We use the little formula x equals negative b over 2a. So we wouldn't technically have to grab the calculator for this. We could just do a little bit of algebra here and put a formula in here. So negative, and I look at this and realize I've got ax squared plus bx, c is 0. I don't have a c back there, and that would make sense because if they're not selling any boxes, they're not going to make any money. So 0, 0 would be on that graph. So this would be negative 73622.5 divided by 2 times negative 1538. 15358. 0.929. And that would give us our x coordinate for that revenue. So I'm going to give you a minute here to punch that in. I better grab calculators. Anybody need to borrow one? That's going to give us how many boxes we're going to sell. Oh, actually, so negative 73,622.5 divided by 2 times negative 15,358.929. What you get? 2.393. So we'll go with $2.39 per box. But that was what they asked. They wanted to know about revenue. So what do we do with that to get the revenue? Plug it in. Yeah. So take your $2.39 and plug it into our simplified revenue. Of course, we're going to round to the nearest box because this was boxes of cereal. How many boxes? $88,227 boxes. Plugging that in. Sorry. Did you use the one that they had with the 2 decimal places or the one we had with the 3 decimal places? Oh, okay. So yours is going to be a little more accurate if you still have the equation in there and everything. Yeah. Because this is boxes. Yeah, because this is boxes. So 88. Oh, it didn't grab my second 2 there. We would take either one because it's a prediction, you know, and things change. It's not going to be exactly that. In real life, you know, it'll be a little bit different. So as long as we're going with our 3 decimal places, we should be okay. All right, so yesterday I said one of these is going to be pretty straightforward. This one is pretty straightforward. This next one also is, but it doesn't appear that way. So what we have to do is be very careful as we move on to the next problem. We've got vertical free fall motion, and it says the height s and the vertical velocity v of an object in free fall are given by this lovely formula. Right there. S of t equals -1/2 gt squared plus v sub naught t plus s sub naught. Oh my goodness, that's a lot of variables. And v sub t equals -gt plus v sub naught. Now the g shouldn't shock any of you who've been in science classes. That's gravity. Now that's part of what happens with this. So t is time in seconds. G depends on whether or not you're talking about feet or meters. We've got approximately 32 feet per second squared, and approximately 9.8 meters per second squared. That's our acceleration due to gravity. And then v sub naught is the initial vertical velocity of the object, and s sub naught is the initial height. So this is one where we have to pay close attention to what variable is doing what. So this says these formulas disregard air resistance, and the value for g is valid at sea level. So we might be a little surprised when our g doesn't come out to be exactly what we see up there, and that's because it's the gravity due to acceleration. So down here, it says the data in table 2.3 were collected in Boone, North Carolina, about 1 kilometer above sea level, using a calculator-based Ranger, CDR, and a 15-centimeter rubber air-filled ball. The CDR was placed on the floor face up. So somebody took this gadget. Texas Instruments makes a lot of these things, and they put it on the floor somewhere, and then they backed up a ways. And apparently, we're supposed to believe they were laying down to do this because they're supposed to be ground level. But they threw the ball upwards, and it hit the CDR. And what we want to figure out is the maximum height of the ball when they threw it, and then the vertical velocity when it hit the CDR. And this is not exactly what the formula gives us. The formula has pieces that give us that. So what we'll have to do is we'll have to come up with a model and then figure out how that fits with that formula that we have. So the first thing we would do, we've got rubber ball data. Where do you suppose that needs to go? Into the calculator, exactly. So I'm going to shut this down for a second so that you guys can get that data in. In the window, we want to make sure we have numbers that are going to allow us to see this data. And our x values in list 1 were from 0 to 0.86. So I just went from 0 to 1. And because they're going to ask us questions later, I thought, you know what, with the y's, I might have a few negatives just so that I can make sure that I can find intercepts and things like that. So I went down to -2, but then the highest number that we had in that one was 1.8 something. So we ought to be able to get away with 2, but I went with 3 just so there's a little bit of clearance. So there it is. And now I want to see that data, and that means a stat plot, because that's how we always get the visual of the data that we put in. Second, stat plots. I'll go into number 1, turn it on, and then I make sure that my lists are using list 1 and list 2, and they were. If they're not, remember you can hit second number 1 for list 1, second number 2 for list 2. And then we should be able to hit graph and take a gander at it. That looks like a parabola. You know, it absolutely has that nice curve that we would look for. In fact, we should be able to get a really, really good curve of best fit for this one. It should be a very, very good one. So now the next thing we want to do is let's find that curve. And in the past, when we wanted it to do regression, we had to hit stats, calculate. So the regression we need is here in this list, but we have to know by looking at it, hey, we should use quadratic regression this time. And quadratic regression is number 5 down here. So that's the one we want to use this time. And again, there's several different types of calculators in the room, so some of us are going to see this, Some of you are seeing just the statement quad regression along the bottom. And let's go ahead and put list 1, comma, list 2. Well, let's stop there. I don't think we're going to need to store this one. We can do it, we can figure it out another way. So let's just go all the way down to calculate. And those that have the older calculators, quad regression, list 1, list 2, and press enter. Let me get that. First thing I'm looking for is the strength of this quadratic regression. And normally, we get a lowercase r. That's the lines. This is quadratic regression. So with quadratic regression, they give us r squared. But it doesn't really make a lot of difference. Because if r is supposed to be close to 1, and we're seeing r squared, it should be close to 1. It is very, very close to 1. So this is a really good line of best fit. Now, if we did want to see it, not line of best fit, curve of best fit. If we really wanted to see it, we could go back and do the variables with our calculating the quadratic regression. So I'll do that up here. You don't necessarily have to do this on yours if you don't want to for the math we're going to do. And then I'll hit graph so that you can see. Very nice. Very nice model. So what we have to do is we have to take that model and use it to answer their questions. So let's go back what we wanted us to do and write down our model. So our model, the 3 decimal places, y equals negative 4.676 x squared plus 3.758 x plus 1.045. So negative 4.676 x squared plus 3.758 x plus 1.045. I'm just going to make a little note up here. We had a really great r squared value of 0.999. Well, now that's definitely not the answer to the question that they asked us. What they said was, use these models to predict the maximum height of the ball and its vertical velocity when it hits the face of the CDR. Well, we could see from the graph it's going to be where the vertex is. I mean, that's going to be that maximum height. So again, we could do this algebraically. X equals negative b over 2a and show our work. Get the x value and then plug it back in so that we'll know that maximum height. Or we could all go back and store it in the calculator. So going back to what I just did was stats, calculate, and quadratic regression number 5. And just get that y variable here. Variables, y variables, number 1, enter. Back down. Now, if you have the older models, you have to put another comma here, and then get that y sub 1 to store it in there. But once it's graphed, we can let the calculator find that max for us as well. And it's going to give us the same answer, might be slightly different rounding than doing this by hand, but second trace for the maximum, number 4. And we're going to meet Blakey on the left side of the hill. Right side of the hill. This is Blakey question was, the ball was thrown upward, landed directly on the face of the device. Predict the maximum height of the ball. Which one of those is right? 1.800. That's the one right there. So 1.800 would be our maximum height. This was metric height in meters. Now, if this is on a test, I'm going to do the algebra, and then I'll double check with the graphing calculator. You know, we'll go ahead and calculate what the x should be, plug it back in, and get that y value if I have time. It's always one of those things we have to deal with on the test is how much time do we have. Now, the second part of this is how are we supposed to figure out the vertical velocity when it hits the face of the CVR? Okay, well, there's a formula for that. Right here. V sub t equals negative gt plus v sub 0. But I have to know what g is. The good news is, my formula matches this. The prediction that I made with my formula matches this. So what we want to do is write above or below what we have, what I have in the red up there. The formula which was g of, or s of t. Yep, s of t equals. And that was negative 1/2 gt squared plus v sub naught t plus s sub naught. Because the formula I have to use is v sub t, or v of t, v sub equals negative gt plus v sub naught. And what I'm trying to do is build a formula that will give me everything that I need. Well, this looks like we just have a little matching to do. Because if this is the squared, to get g, I know negative 1/2 g has to equal this number. This variable and this variable, it doesn't match. It doesn't matter that one is a t and one is an x. They don't have to match. But this has to give me that negative 1/2 g. And we can solve that pretty quickly and easily just by multiplying both sides by negative 2. We can get g. So we need negative 4.676 times 2. Let's get 9.352 meters per second squared. Okay, that's helpful. That can go right here. So now the next thing I'm looking for is, how about v sub naught? That was the other piece I needed for this formula, was this little v sub naught. What's that? 3.758 right here. That's v sub naught. So now we have a little formula for v of t, negative. We've got 9.352, and we've got our, oh yeah, I need the negative in front of that because this was a negative v. Negative g, there we go, plus that. Now, people are you serious? Okay, well we have a little bit left for this problem. Just a little bit. We found the maximum height. Let me uncover this. I got it. I didn't think going over the test was going to take that long. There it is. So take a picture if you need to. I will put it on the completed notes on Schoology Rats. And we only have like 2 steps. And we're done.